Finally, let us now see why spiral galaxies are spiral. Obviously, the spiral arms are the defining feature, and there's some important observational facts about them. Probably the most significant of them is that they're seen only in disks that do contain interstellar material, the gas, which then causes star formation. There are disks which do not contain much gas. Those are the S0 galaxies. Another important clue is that they're seen in young stars. And since young stars tend to last less than a full rotational period, it suggests that possibly the spiral arms are transient phenomenon, that they actually last less than typical rotation periods of these galaxies. And something that is a little tricky is that when you look at the spiral galaxy, you have an impression of a vortex and that they rotate in the sense of you would see in, say, water going down the sink. They do, except that they move at half the angular speed of the disk. So the disk of the galaxy rotates in the same direction as you'd infer from winding of the arms, and so do the spiral arms, but at half the speed. So relative to the disk, the spiral arms are actually moving in the other direction. They move as if they're scooping up the stars, counterintuitive to what you think. Now, the important feature to remember here is that essentially all galactic disks have more or less flat rotation curves, meaning the linear velocity is roughly constant as a function of radius, which means that the angular velocity goes as 1 over the radius. And so if you were to start with, say, straight features directly through the galactic center, due to the differential rotation, it will naturally produce something that looks like segments of spiral arms, which actually presented a dilemma initially on, because if somehow spiral arms were constant, because of the differential rotation, they'll keep winding and winding until they look like a really tightly wound spiral, and that's not what we see. An interesting way to approach this is as follows. Imagine that stars move around the center of a galaxy on elliptical orbits, as roughly they do, but that subsequent orbits at larger radii are shifted a little bit. So it kind of looks like this. You start with one, then keep adding concentric but tilted orbits, and by the time you're done, you can see that there is something that looks like two spiral arms. And in fact, this is roughly what happens, but the question is why? The answer why is the so-called density wave theory that was developed in the 1960s and 70s by Lin, Xu, Toomer, Kalnice, and others. And the upshot is that spiral arms are density waves in differentially rotating disks. If you were, say, to drop a rock in a pond, it will have circular waves going away from the center. But galaxies are not stationary ponds. And if you were to make a perturbation in a differentially rotating disk, like disk of spirals, what you get is not circular waves, but spiral waves. The reason why they persist at all is resonant motions. You can decompose motion of any star around center of a galaxy to first approximation as circular orbit with some perturbation. And the perturbation can again be approximated as, say, a star wobbling around that radius, in other words, making circular orbits around some hypothetical node on the central part of the orbit. That resembles epicycles from Ptolemaic theory of solar system, and in fact those are called epicycles. So if you have the exact match in the numbers of orbits around that center of the epicycle and its motion around the center of a galaxy, you will have amplification, and that is exactly what's happening. So if you look at angular frequencies, omega, not to be confused with density parameter, and then look at the epicyclic frequency, again angular frequency, then divided by integer number, which is usually a small one or two or something, then the first two resonances are called the Lindblad resonances, and they actually are the radii in which that particular rotational frequency occurs, from which or to which spiral arms extend. And since usually the first harmonic or first resonance is the strongest one, this is why we mostly see two-arm spirals, although we do see, for example, four-arm spirals and so on. So another way to phrase this is that spiral arms are density waves which are really resonances of perturbations in these differentially rotating disks. So remember the orbit crowding diagram. That is more or less what happens here, where an elliptical orbit can be really decomposed as circle plus an epicycle that makes exactly one turn as the big one turns around. And so that's what causes the elliptical shape. Now the orbit crowding really implies that there is going to be a density pileup, and that's exactly what spiral arms are. Now these waves are moving relative to the underlying disk, gas and stars. And so as the waves hit a material, they are compressing it. Compressed gas is liable to make stars, which is why we see star formation associated with spiral arms. So this is why star formation can be triggered by spiral density waves. That's not the only way in which we can trigger star formation in disks, but obviously it works. And there'll be stars made of all different masses, but the most massive stars, as you probably know, are the most luminous ones, and they live the shortest. So it's the shortest lived, most luminous stars which haven't had chance to drift away from the wave before they explode that will delineate pattern of the spiral density waves. When you look at the bluer wavelengths, which are more susceptible to the radiation from young, hot, luminous stars, you see very prominent spiral density patterns. If you go to the redder wavelengths, say near infrared, where the light is dominated by the older red giant stars, the spiral arms are still prominent, the density wave is still there, but not nearly as much or not nearly as sharp as you would see in blue or ultraviolet light. So schematically, you'd expect things to look like this. There is the spiral density wave that moves relative to the underlying disk in the opposite way of what you'd think from, say, water going down the sink. In other words, the arms are scooping up the material, so the leading edge of the wave is the inner part of the spiral. This is where density wave compresses the gas, molecular clouds, makes dust lanes, and then inside of them there'll be star formation. So you'd expect to see dark lanes on the leading edge, which is backside of the spiral arms, followed immediately by regions of star formation, and then kind of more diffuse bluer stellar population as you go towards the trailing edge. And now let's look what that looks like in real life. So this is a picture from Hubble Space Telescope of, I believe, M101, bright nearby spiral. And this is exactly what you see. The inner part, which is the leading edge of spiral arm, is where you see the dust lanes. And then the red dots and blobs that you see in the dust lanes or immediately past them are the regions of young star formation. Those are H-alpha nebulae ionized by young stars. The young stars burn out through the dust, dissipate it, and then you see luminous blue stellar light, and then kind of fades away as you go towards the trailing edge of the spiral. So the theory predicts exactly this. To summarize, spiral arms are density waves that occur in differentially rotating stellar disks. They will compress gas. That will lead to star formation at edges where gas enters the spiral density wave. Stars themselves will simply pass through the density wave, just like water molecules pass nicely through waves in the water. And this dynamical theory is very successful in explaining the global properties of spiral galaxies. But it's not perfect. First of all, it doesn't say why were the waves to begin with. Some sort of disturbance has to happen. And one possibility is that encounters between galaxies create such a disturbance. That's entirely possible. Another part, which is a little more difficult, is that not all spirals are perfect two-arm spirals. There are detached spiral arms, spurs, things like that. So additional mechanisms might be responsible for creation of such patterns. Now, whereas the theory predicts exactly what we should see in, say, two-armed grand design spirals, as they're called, there are other types of disk galaxies, spirals so to speak, in which the patterns are much more diffuse. They're called flocculent galaxies, that they almost have no spiral arms, but they certainly have patches of star formation and even maybe little segments. And they may be caused by a different phenomenon, namely differential stretching, just like we addressed it in the beginning of the lecture. So that's it for these galaxies. Next, we will start talking about elliptical galaxies.